So again, what I've done here is to use our formula for the sum of the series when it's convergent, whatever is the common factor, and then 1 over 1 minus the common ratio. Notice when your common ratio is negative, like it is in this one, and you do 1 minus, your denominator is something bigger than 1. And so you see what it is it's 5/4. So you have 5 times 1 over 5/4. So invert and multiply, and you have 5 times 4/5, which is the 4. Well, one of the reasons that this book and the other books do things the same way, really, start talking about the geometric series, aside from the fact that we can get a formula for the sum if it's convergent, is that you can relate the geometric series to repeating decimals, which is a way to understand our number system a little better. And so we'll do that in a second. So if you look at problem 19 in I don't know really why I'm writing 16 here. It's not chapter 16, it's chapter 10. So this should have been 10-2, number 19, and this should have been 10-2, number 10. Anyway, suppose you write decimal point 23 and put a line over it. What you mean is 23 repeats forever, like that, 23 all the time. And if you think about what that means, the first 23 is there, then the next one you have 0, 0, 2, 3 added on, and then this one is 0, 0, 0, 0, 2, 3, like that, and so on. So if you want to think of it as fractions in order to look at things as a geometric series, then this one is 23 over 100, this is 23 over 100 squared, 23 over 100 cubed, and so on. So then you see 23 over 100 would factor out, so that would be like the A if you're going to do the sum of the geometric series. And factoring that, then you have 1, and then 1 over 100, and 1 over 100 squared, and so on. So your common ratio now is 1 over 100. And for example, if the problem had been like problem 20, where you have 3 repeating decimal repeating in groups of 3, it's 2, 3, 4, or whatever it is. You can look at problem 20 and see. I know it's groups of 3. You'd play the same game, but your common ratio would be 1 over 1,000. So it's 1 over however many digits define the size of the group of repeated digits. So then here's your ratio 1 over 100. So your sum is A, 1 over 1 minus the common ratio. And do your fractions, 100 minus 1 over 100. Invert and multiply, you get 23 over 99. Now I invite you, those who have brought a calculator, fire up your calculator, put in 23, divide by 99, and set your display to display as many digits as it will display, and see if it isn't so. This is mathematical laboratory, you see. That's what labs are supposed to do, is to have you run through some kind of thing and see with your own hands that it really does that, and so on. And you see, those of you who are doing this, you see it does work, right?
Mm-hmm.
If you do 23 over 99, this is what it will show as far as the screen will carry it. So there is an easier method than this, which they should have taught in 143 or 147. Again, I don't know whether they did, or in high school if you took your math there. So without calculus and the geometric series, just call your original decimal x and then multiply by whatever is required to shift the decimal point to the next group of repeating digits. So by 100 if they're repeating in twos, by 1,000 if they're repeating in threes, by 10,000 if they're repeating in fours. So 100x then gets you the first pair off to the left of the decimal point, and then everything is identical to what you called x. And the idea is these are infinite decimals, so you can multiply by 100, and you're not going to run out of 2, 3 pairs to match up with the original. And then subtract. And you see these all cancel out to the right of the decimal. So 99x is 23, and there you are, 23 over 99. So you can actually get the fraction that corresponds to an infinite repeated decimal without doing calculus. But anyway, if you approach it from a calculus point of view, what you're working with is summing a geometric series. Okay, again, I don't know why I kept thinking this was chapter 16, but anyway, problem 28 wants us to test for possible convergence using this nth term test. Remember, that's the thing back here, that if the series converges, the limit of the general term of the series has to be 0. So if you get your limit of your general term not 0, it diverges. So that's what these are looking for. Just a second here. So if you look at problem 28, you'll find that this is what it is. And what we want to do is see what the limit is of this general term. And you don't necessarily, in finding the limit, need to multiply these out and these out, but that's one way you can do it. And if you do it this way, then it's easy either to do L'Hopital's rule, where, as we were saying yesterday, you think of the related variable x for the envelope and see a 0 over, well, an infinity over infinity form is what this would be, because you're talking limit as n goes to infinity. So you treat this the way you would with the variable on the envelope, so you can differentiate it. Or, if you prefer, you can approach this as a rational function, as in Math 143 or 147, where they tell you to divide by the highest power in the denominator, and then know that 1 over n squared, and things like that go to 0. Either way, you see you get a 1 and a 1 over n, and a 1 and a 5 over n and a 6 over n squared. if you divide top and bottom by n squared, and so you get 1. The point is your limit is not 0, so it's divergent. So this is a divergent series by the first test on the long sheet of paper. Okay, again, this should be 10-2 and not 16-2. 35 through 37 are what we call telescoping series. You think of something like the Navy of a couple hundred years ago with the sailing ships and the spyglass like this, looking for Napoleon's Navy, say, or something of that kind, and then the spyglass, the telescope folds down, okay? So a series like this does this because if you first write some terms, say n is 1, you have 1 over 1 minus 1 over 2, and then when n is 2, you have 1 over 2 minus 1 over 3, and then when n is 3, you have 1 over 3 minus 1 over 4. Well, notice what happens if you take away the parentheses. You still have your 1 here, but those two cancel. So you have minus a half and plus a half. Then you have minus a third and plus a third. You'd have minus a fourth and plus a fourth. And so it telescopes in that way that the telescope collapses to the first term, 1, and then over here, the last fraction you'd have in your partial sum, 1 over n plus 1. So your sequence of partial sums, then, is the sequence of expressions like this. And so your series, then, has the value which would be the limit of this sequence Sn of partial sums, and that limit would be 1 minus 1 over infinity, so you would get 1. So the original series then converges to 1. So sometimes you have a kind of series where there's some trick like this that'll let you write the sequence of partial sums. Often you can't really get a convenient formula for the typical member of your sequence of partial sums. And if you can't get a formula for it, you can't take the limit directly to see if it's finite or infinite. But you can still use one of the tests that we're developing to tell if the series is convergent or divergent. If it's divergent, you can't really do anything with it. If it's convergent, then you could calculate the first so many terms, some finite number, and often you can get some kind of estimate on how many terms are close enough for government work, say, that kind of thing. Look at problem 37, which also telescopes. You have log square root n plus 1 minus log square root n. And so your first term, when n is 1, you have log root 2 minus log root 1, and of course that's a 0. Then when n is 2, you have log root 3 minus log root 2. Then when n is 3, you'd have log root 4 minus log root 3, and so on like that. So then what will happen is that these will cancel out in pairs. You see, for example, you know first of all that this one is 0, and then you're doing this. And back here, you've done that one. So, for example, when n is 3, all that's really left is log the square root 4. And if you carry that idea forward, for n, what's left is log square root n plus 1. So your partial sums collapse to being log of square root of n plus 1 for the nth term in your partial sum. So your limit will be whatever this limit is. Well, what is the limit of log of the square root of n plus 1? Well, you can say the square root is the half power, and so it's half limit log of n plus 1, and log n, or log x, just keeps climbing. So your sequence of partial sums then diverges. So this is an infinite series which you could not really use because it's divergent, so you wouldn't want to build anything based on calculations of the first few terms of this series. It has to be a convergent series to say, well, there's a true number for the sum, and the first 10 terms are within 1% or whatever it is that you want. Okay, let's look at why this harmonic series thing diverges, even though the nth term certainly does go to 0. Now, the proof that I have up here that spreads across the top of the board is the first way that people studied this thing and saw the idea that the total was more than any number you'd want to name. People took the approach that I'm about to go through with you quite a long time ago, long before the era of Sir Isaac Newton and Leibniz and calculus as we know it. The first people to study this, again, and I think they were also people who were interested in music, were monks in various abbeys in Europe, close to 1,000 years ago. Actually, if you study music, some of the music from that long ago is very fine music also. So they had ideas of harmonics. And I think the name goes clear back there. But people that were working then reasoned like this. You see, you're taking all these fractions, always with a plus, and you could look at the first pair of them. What you do is you look at them in groups that where the denominator is a power of 2. See, 2 to the first power, 2 square, 2 cubed, 2 fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, and I ran out of energy to keep writing, but you see the idea, okay? So that's more than 2 halves, so that's more than 1. This is more than 2 fourths. See, a third is more than a fourth, so that's more than 2 fourths, which is a half. Then a fifth, a sixth, and a seventh are more than an eighth, right? Bigger the denominator, the smaller the fraction. So that's more than, count them, 1, 2, 3, 4 eighths, which again is a half. You're comparing all of these groupings with a half, and what you're seeing is that each of these groupings is more than a half. You don't need to know how much more. You could figure it out, but you don't need that. See, so a 9th through a 16th, count them. There are 8 fractions there, better be. And so each of these is more than a 16th, so altogether you have more than 8 16ths. And then 17 through 32, there's 16 terms there. So it's more than 16 32nds. And then this one is more than 32 64ths. And this is more than 64 over 128. So what you have then is that when you've reached the fraction like this one, 1 over 2 to the k, 1 over 2 to the, what is it, 7th, I guess, your sum is, you see, what you've done is you have more than a half, more than a half, and a half, and so on. So you have as many halves as is the exponent on the 2. So more than k halves, which in this case would be 7 halves, so it's more than 3 1/2, and so on. So the limit then of your sum is greater than the limit of k over 2 as k goes to infinity, and you see that's certainly divergent then. Okay? So you could buy anything if you had enough $50 stacked up. You wouldn't want to carry it, but you could, is the idea. So that's the original way that people saw that the harmonic series diverges. And even though we have a much more efficient way to see it, which is off over here, I think this is worth going through because it gives a more intuitive feel for what divergence really means, I think. Okay, so the divergence is very, very slow. You see, you've taken 128 terms to get more than 3 1/2 out of it. And that's because this harmonic series, thought of as a p-series, is right on the line between convergence and divergence. I've said that before this morning, and you might wonder, well, how do I know that? And that comes from section, here I got the 10 right, 10.3, and the integral test, which is here. So we'll do this much of 10.3 here so that we'll have the idea in your mind of the integral test, and then we'll come back to the integral test next week. But for the integral test, we suppose remember that when we're talking about convergence and divergence of a sequence, as yesterday and as we reviewed today, the sequence is like the cars on the train track, and the train track is your curve with a continuous variable x. So thinking of your general term in your series as f of x then, which would be your envelope, if you have f of x positive and always decreasing from some point onward and continuous, then you can do something like this. So the envelope now in my picture here is the green, is f of x. And I'm sure it doesn't surprise you that somewhere I have a handout for this. And I guess I put that over here. We think then of 1, 2, 3, 4, 5, and so on for our ends. And then the A1 and so on would be the height to the curve at 1. So that would also be the first term of the series. And then A2 would be the second term. And A3 would be the third term. And so on like that. So then look at the areas. My spacing here is 1, 2, 3, and so on. So these rectangles are 1 space wide. So the area equals the height. So in red, I have taken the height to the curve at the left side of the rectangle. So the first term of the series is my function value at 1, where I'm thinking of the envelope function for the series. And my first term number is also the area of this first rectangle in red. So I have A1, and I have the red color and the arrow pointing at this rectangle clear up to there. And in the same way, then A2 is the area of this rectangle, and A3 is the area of this one, and A4 is the area of this one, and so on. On the other hand, if you go over to 2 and get A2, which is the height of this red one, and go back to the left, there's a purple one, which is the same area that this is, that I've indicated here and written A2 in purple. And then in the same way, A3, which is the height here, is 2 things. It's the area of this red one off to the right, and it's the area of this purple one off to the left. And so on in the same way. And then your curve, you see, cuts kind of in between. So if you look at your partial sums then, what you have is that the sum 1 to n, which is also the sum from 2 to n plus the first term, is less than or equal to a1 plus the integral 1 to n f of x. Remember, the f of x is your envelope, so x is a continuous variable. So that you can integrate it. And the integral would be the area under the curve from there to there, the area in green. So then the integral, on the one hand, is less than or equal to the sum of the areas in red. See, if you look at the 4 red areas that I have, your sum A1 plus A2 plus A3 plus A4 is more than the area in green, which it's more than this area. So this here in green, which is the area of your integral, is less than or equal to the sum AK of the red rectangles. So therefore, if your integral diverges, this is thinking of convergent and divergent integrals as in the end of chapter 8, where we had these improper integrals and we took the limit as, say, from 1 to infinity and so on. If the integral is divergent, then your series diverges, because your series, the whole thing, starting with 1, is the 4 red areas, which is more than the green area. On the other hand, if the green area is finite, it's more than the purple area. And so what you would have then is that the first term plus the purple area, which is A2, A3, A4, the first term plus the purple area is then less than or equal to the first term plus the integral. So if the integral is convergent, you can add the first term, and that's still a finite number, and that'll be more. So what this finally says is, if the integral converges, that much is finite, and the series converges. So let's end with our application to the harmonic series. For the harmonic series, then, your f of x is 1 over x. And so if you look at the limit, doing this as an improper integral, like chapter 8, of the integral 1 to b as b goes to infinity, you can integrate dx over x, you get log x, so then you have log b minus log 1, and take the limit of your log, and that's divergent. So your harmonic series diverges because the sum of 1 over n is more than the integral 1 to infinity dx over x. You see, that's what we have here, that the sum of all of the red rectangles is more than the integral, which is the area under the green curve. So if this diverges, that's more, so the series does. And as I said, if this converges, that's more than the sum from 2, sum of the purple rectangles, and then you can add a 1 there, and which gives you the whole series. So a1 plus the integral is a number if the integral converges. So you can prove the harmonic series diverges very easily with the integral test, but you have to have calculus to have integrals. And as you see, you can prove it without calculus, really, which people did first. That's some of the oldest mathematics that we have, actually, other than the Greek geometry. Well, I think that's enough of this for this week, and next week we'll go over here. So we're thinking about what we call an infinite series. This is the section 10.2, and this is your summation symbol that tells you to add. So it means A1 plus A2 plus A3 and so on like that. So we define then the sequence of what we call partial sums in the way that I'm showing you. The first term in the sequence is the first partial sum, so it's the sum of the first n equal 1 terms. So it's the same thing as the first term of the series. Then the second partial sum is the second term in the sequence of partial sums, so it's first term plus second term. So in other words, sum of the first two n equal 2 terms. Notice that the A1 is the same as the first partial sum, first term in the sequence, so the second term in the sequence is also the first term of the sequence plus the second term of the series. In the same way, the third partial sum is the sum of the first n equal 3 terms, and it's also A1 plus A2 then, plus A3, so it's also S2 plus A3. Always the difference between Sn, sum of the first n terms, and Sn minus 1, the sum of the first n minus 1 terms, this minus that will be the nth term. This is an important point. This is what I'm saying here. The sum of the first n terms, which is the nth partial sum, is the sum of the first n minus 1 terms, which would be A1 through AN minus 1 plus AN. So that AN, the nth term of the series, is the difference between the two partial sums, the sum of all n terms and the first n minus 1 terms. So what that means is that if you're talking about a limit as n becomes infinite, since both of these are on the track where the train goes to the same station, in the limit, these two are both equal, so the limit then of the general term of a series has to be 0, if it's a convergent series. Because convergent series means that the sequence of partial sums converges. That's what I'm saying here. Definition: series converges to some number L if and only if L is the limit of the sequence of partial sums. In other words, the partial sums are the train cars on a track that we could call the envelope, and that track is actually has a station to which it's going. That's what you'd call your limit, as opposed to just going on to infinity. If you're thinking of these as positive term series, which is what we're thinking of in chapter 10, then adding up positive numbers, either there's a horizontal asymptote type of graph, or else it's a graph like the square root of x over there that just keeps climbing. Actually, with definitions, any definition that you make is a if and only if type of thing. So the S sub n then is the partial sum, k equal 1 to n, of the terms in the series. So as I've said here, it's the partial sum. Think of it written that way. So if you consider the general term of your series, which is the difference between these two partial sums, if it's convergent sequence, then this has limit L, also then this has limit L. That's what I was talking about in the center of the room. And so does this one, all but the last two, and so on. So then the limit of your nth term, or general term, of the convergent series is the limit of the sequence Sn of partial sums minus the limit of all but the last term in the partial sum, and those are both the same number if it is convergent. And therefore, you get this theorem that if the series converges, then the limit of the general term is 0. And this is important because the converse is false. For example, here's this divergent series. It has a name. It's called the harmonic series, and I'll prove to you in a few minutes that the thing is divergent. That is to say, if you take all of the numbers, the counting numbers, 1 plus a half plus a third plus a fourth plus a fifth, you can make them add up bigger than any number you want to name if you live long enough to do it. You won't really live long enough to do it, but still, it's possible. So that means that if your nth term limit is not 0, the thing is going to diverge. But even if your nth term limit is 0, the series doesn't necessarily converge. It's not that easy. We have in this chapter various tests for convergence. There isn't any of them that will work as a practical matter for every single situation, but what we will find as we go through this chapter is that of the various ways to test for convergence, usually there will be something that will work. There will be for the problems in the book, anyway. But if your nth term limit is not 0, the thing diverges. Period, end of story. Because the two sequences of partial sums, n terms and all but the last term, both have the same limit if it's convergent, and therefore that means that the a sub n is L minus L and has to be 0 in the limit. So if you have a series, say, that's 1 plus 1 plus 1 plus 1, that has to diverge because your general term is 1, and that isn't going to 0 in the limit. And that only makes sense if you take 1 plus 1 plus 1. If you have enough dollar bills, you can buy anything. You've got enough of it, right? So, notice the long sheet of paper which you got yesterday or just got this morning, and it's copied from another book, obviously, and it has most of the various tests that we will learn to work with in this chapter for convergence of a series. And you see the very first thing on the page, on the top of the page, is this nth term test. If the limit of the general term is not 0, series diverges. So it proves divergence if you have a divergent series where the nth term doesn't go to 0, but it does not prove convergence because, as I said, here is something where the nth term, the limit of 1 over n is certainly 0 as n goes to infinity, but that thing actually diverges. Okay, and then you see there are these various tests. What the book is doing that I've copied here is to list the tests more or less in the order in which you learn them as you go through chapter 10 or whatever chapter it was in the book that I've copied. but it isn't necessarily that after you've learned all of the tests, that the comparison test, which comes next here, is the very first thing to try. It's harder to do, actually, than some of the others. So it isn't that they're in order of preference, I think. It's just how they did it, kind of. So we won't learn all of these tests today, obviously, but that's what we'll do the rest of the month. Happy April Fool's Day, by the way.
Oh, yeah.
Okay. So, common types of series, there are various series that we study enough that we give them a name, are what we call the geometric series, which we're about to talk about. And there are the p-series, which looks like this, 1 over n. So n is the variable, and the exponent is some fixed power. So this could be, for example, 1 over n squared, or 1 over n, where p is the first power. So this harmonic series, which this one is called, is a special case of the p-series, where p is 1. Or the p could be a fractional exponent. You could have 1 over the square root of n, or 1 over the cube root of n, stuff like that. It turns out that the p-series converges if p is greater than 1, and it diverges if p is less than or equal to 1. Notice, again, if p is equal to 1, you have this. So this thing is right on the edge between divergent and convergent, if you think of it in the context of being a p-series. So what it does is it diverges, but it adds up very, very, very slowly. Okay, so let's talk about the geometric series a little bit.
I have a question. I'm sorry.
Yes.
Is that harmonic? Is that I can't find the word now. Is that in comparison to something else? Is that?
No.
Okay.
It just is a kind of a happen-so.
Okay.
That there are series that people have called geometric
Okay.
for a long time. This one has been called harmonic for a long time, and the reason I think actually is related to music,
Okay.
in the sense that the 1 over 1, 1 over 2, 1 over 3 is something like harmonics of sound, or at least somebody thought so.
That was my next question. Is that the same formula used for sound waves and for like electrical waves? Okay.
Yeah. So that's why the harmonic name. And the more general case, if you put an exponent on the end, is called p-series, and I don't know who in the history of math decided to call it that, but somebody influential enough that it stuck, and I really honestly can't tell you who. And the harmonic series then, where p is 1, is a special case. So those are series that are named enough that it's worth at least saying, and you'll see that in the book. And there are others too that actually have a name. Okay, so back to the geometric series, as it's called. It's called geometric if there is a fixed ratio, R, between a term and the next one. You see, if you took the term AR squared and divided by the term AR, everything would cancel except you'd have R, which is the ratio between this term and that one, or between this term and that one. So you And again, I'm not just sure who decided to call that kind of behavior geometric, but that's a name that you see. So if you have the first n terms of a geometric series, this is term number 1, 2, 3, so on through n. You have a, where a is going to be a common factor. R, AR is the second term, AR squared is the third term. So the term number is one more than the exponent. So then AR n minus 1 would be the nth term. And if you multiply by R, you'd have R times whatever is the sum of the n terms. And multiplying by R, you see what you do. You take this times R, and you get this, which is like the second term. This times R, you get this, which is like the third term of what you started with here. Then the term behind this, last one here, would have been AR n minus 2. You multiply by R, and then what you get matches this, and then R times this is out over here, and there's nothing up above to match this. So then if you take top line minus bottom line, you have Sn, whatever is your sum of these n terms, minus R times Sn, and these cancel when you're subtracting. You go vertically, and it leaves you the A minus the AR n. And then you can solve like in algebra, so you factor the Sn, and the other factor is the 1 minus R. So the sum then of the first n terms of a geometric series built like this would be given by this formula as long as R is not equal to 1. Of course, you can't divide by 0. And if you did, you see you just get 0 over 0. Well, this is something that should be taught to this extent in Math 143 and 147. Now, whether they did it when you took it is another story, but that's that much you could do without really any calculus. So where calculus comes in now is, see, this is your formula for the terms in your sequence of partial sums of a geometric type series, again, assuming R is not equal to 1. And so then the sequence of partial sums, which are given by this formula here, will converge to whatever this limit will be. If the infinite geometric series is going to converge, and it'll diverge if the sequence of these things will diverge if the series diverges. So if this limit is a finite number, then you'd say that's the sum of the infinite geometric series, where you don't stop after n terms but just keep going, a plus AR plus AR squared on forever. And if you can't get a limit number here, then you say the thing diverges. Well, what turns out to be true about, you see, where you're taking this limit, the A is a fixed number. Certainly 1 is, and the R is the ratio between successive terms. So the variable here that's going to infinity is this R to the n. And if you look on the summary sheet, down there in where it says key formulas, and you see my handwriting, under limits, limit r to the n is 1 if r is equal to 1. 1 to the n is 1. It's 0 if the magnitude of r is less than 1. And it is divergent otherwise. In other words, it's infinite if r is greater than 1. So we have then that this term would become 0 in the limit if and only if the magnitude of r is less than 1. And so then your infinite geometric series, which looks like this, some common factor, and then r to the n for some fixed r that's less than 1, will become the a 1 minus 0 over 1 minus r. So your geometric series converges to this when r magnitude is less than 1 and diverges otherwise. Suppose r is equal to 1. Remember when we did the derivation back here in Math 143, we couldn't divide by 0. So go back and think about what you have if r is equal to 1. And you see what you have is a plus a plus a plus a. So when r is equal to 1, the original series looks like that, and that diverges because the nth term is a, and it's not going to 0 in the limit. That's why this nth term test is the first thing on the page. So that lets you say that when r is 1, what you get for your geometric series is divergent. Okay, if you look at the first of the problems in section 10.2 homework, you have, not surprisingly, some geometric series, because that's the first thing that you really have a way to sum. So problem 1 is 2 plus 2/3 plus 2/9 plus 2 over 3 to the n minus 1. So your common ratio is 1/3. If you take, there are two ways you can see that. Take a term, multiply by 1/3, you get the next one. Take this times 1/3, you get the next one, and so on. Or take a term and divide by the 1 immediately to the left, and your quotient is the common ratio. Okay, that's less than 1 in magnitude, so it's convergent. And that means then that your series, if you write it with the summation, it would look like this, is, according to my formula, if you have a common factor, which is the 2 here, see that's the a, times 1 over 1 minus r. Okay, 1 minus 1/3 is 2/3. Invert and multiply, and the 2's cancel, so it's 3. Well, you can kind of believe that. You see, you're starting out with 2, and then 2 and 2/3, and then you're adding 2/9 to that, and then 2 over 27, and so on. So the first 3 terms, you're almost to your sum, and then you're creeping on a little closer ever so slowly. This is generally what these things are going to do. Generally, you don't have to take too many terms of a convergent series to be close enough for government work, as the saying goes, right? And so take a look at problem 10. Okay, this one is also geometric. Notice, however, there's a sign alternator. If you were here yesterday, we talked about sign alternators that'll make the terms go plus, minus. Minus 1 to the nth will do that, because when n is even, it's plus, and when n is odd, it's minus. And so if you start with n equals 0, which is how the problem is written, something with a 0 exponent is plus 1, and 4 to the 0 power is 1, so the very first term in the thing is 5. Or if you want to, you can factor the 5 out, and then your first term inside the brackets is 1. And then when n is 1, you get a minus 1 to the 1 power, so it's minus 5 over 4. And then with the 5 factored out, you have minus 1/4, then plus a 16, and so on. So you can see that the thing is 5 more or less, and that it's probably less. You see, you're starting 5, and then you're taking away 5/4, which is 1/4, so you're down below 4, actually. And then you're adding 5/16 to that. So it isn't too surprising, maybe, that the formula tells you that the sum of the thing is 4. And you see, you wouldn't have to take too many terms to get there. Sequence idea, which is what we worked on yesterday, as you know, if you were here. And so this is the same picture saved from yesterday. You can compare the graph of square root of x, where you're thinking of that as a continuous function and x is a continuous variable. Now, what you mean by a continuous variable, as we said yesterday, is that it takes all values, the values for all real numbers then, that are in an interval. So, for example, the interval from 1 to 9 that I've drawn here, if x is greater than or equal to 1 and less than or equal to 9, it's taking the values of all real numbers, all the decimal numbers that there are. So that's all the fractions and the whole numbers and all of the numbers that are decimal numbers but not fractions, which you call irrational, cannot be written as a ratio of two integers. Then, in contrast, when you talk about a sequence, often you write n instead of x, where n is what we call a natural number, which, as I was saying yesterday, is 1, 2, 3, like that. What's natural is the fingers and the toes. So there aren't any numbers bigger than 20, right? Okay. And so a sequence, then, is a function, the same as square root x is a function. What's special about it is that it has values only for 1, 2, 3. And if you want to look at it over just a limited interval, then typically you write your function formula the same as you would for the continuous variable. You put the braces on the sides, and you say where you start, where your interval starts then, and where it finishes. So the values here would be a set of just 9 values, which would be the 9 green dots. So its graph then would consist of the separated points. And on at least a couple of the different handouts from yesterday, you see that you see these sequence graphs where you either have just the isolated dots or a situation like this with the use of different colors to show a sequence and the corresponding graph of a continuous variable x. So the curve that you get using the continuous variable x is also called the envelope. So the analogy that I was using yesterday is a train on a track, and so the envelope or graph of the continuous variable is the track, and the train, assuming it's going to stay on the track, has to go where the track goes. Okay, so that means that whatever you'd mean by a limit of a sequence, say as n becomes infinite, is what you'd mean by the limit of the envelope curve, because just as the train goes where the track goes, so the sequence goes where the envelope goes. So if the envelope curve is one that's always increasing, like square root of x is, then the sequence corresponding to it, square root of n, in the limit as n becomes infinite, would become infinite. So we would say it diverges. On the other hand, if your envelope has a horizontal asymptote, y equals L, then its limit would be L as x, the variable for the envelope, goes to infinity. Then for the corresponding sequence, the limit would be whatever that number would be that I've called L. So the concept of sequence and limit of a sequence, it has fundamental importance in chapter 10, because what we're going to do today is talk about the sequence that we form from partial sums of an infinite series, especially a positive term series. And so if the sequence of partial sums has a limit, that's what we call the sum of the series. And as I said yesterday, the reason we care about the sum of the series is that the functions for which we have to get values out of a table, or now out of a student scientific calculator like the trig functions, are all computed as sums of infinite series. Turns out if you have a function for which you can write all order derivatives like sine and cosine and log and so on, then you can write a series, and that's what we'll learn how to do in chapter 10, that'll represent that function, and then the values, the sums of the series will give you the sine of 29 degrees or log of 2 or whatever it would be that you want. Your calculator just gives you the numbers now, so it's natural to not think about, well, what's the calculator really doing? But what it's really doing is summing the first few terms of the appropriate series. It doesn't have a table somewhere inside the calculator with busy little elves turning pages madly and displaying the answer for you. What computers do best is to compute the way that people did to make the table, and what they do worst would be a table lookup type of thing. Before the world of student scientific calculators, the books all came with tables in the back of the book, and then the student and the fingers were the busy little elves looking up the numbers. In a way, it's too bad that the books don't still come with a table of some sort, just so you'd see what I'm saying a little better. As I was saying yesterday, if you take statistics, a lot of the functions you work with there are still something you look up in a table in the back of the book, because the calculators don't come with the appropriate program to get the values for functions that you work with in statistics, at least not a student scientific calculator. So anyway, this is a kind of rundown on yesterday's class related to the sequence idea. So we'll go on. Notice here I have my drawing, my train track, and my envelope curve, and what I'm doing here is thinking of the same sequence, S subscript n, and saying that if you think of the value, the natural numbers, 1, 2, on up to n, if Sn is there, Sn minus 1 would be just one car in the train behind, or one step behind, so it would be there when this one is here. And Sn minus 2 would be another car behind, and Sn minus 3 would be another car in the train behind. But they're all on the same track, and they're all going to the same place. So if the limit of Sn is L, which would be the horizontal asymptote for the original envelope graph, which is like the, let's say, the train station, if the limit of Sn is the train station, which is this asymptote, so is the limit of Sn minus 1, Sn minus 2, Sn minus 3. They'll all get there. It just takes a little more, well, if all of the people are going to get out of the train at exactly one point, say like search and seizure that may be coming for all of us, then these people can get out at the station, and the others have to sit patiently. Then the engine chugs ahead, and then these get out, and so on like that. This may be a world that we'll live in, the way things are going. So in that sense, all of these sequences have the same limit. They just get there at a little different time. This proves to be important, this concept that Sn and Sn minus 1 have the same limit in what we're going to do in just a few minutes. Okay, just a minute and we'll go on.